All right, so we first did section 6.1, which was about a distribution, confidence interval, and hypothesis test for a single proportion. And now we're in 6.2, where we're thinking about the distribution, confidence interval, and hypothesis test for a single mean. So just like last time, I'm going to do a derivation to show you that the formula that's on the formula cheat sheet didn't just come out of thin air. And once again, I'm not expecting that you can reproduce this derivation. I just want you to believe me that it can be done. So let's say that x is a random variable. And then we're going to say that the mean of x, the expected value, is e square brackets of x, and sigma of x is the standard deviation of x. And now we're going to take n observations and define a new random variable. And this one is going to be called x bar, which is going to be 1 over n times the sum from I equal 1 to n of my original x of I. So I'm going to add up a bunch of x's, and then I'm going to divide by n. That's how we find the mean. And so we're calling this a random variable, big X bar, but it's basically just like all the other x bars we've seen before. And then what we're interested in is the expected value and the variance of this random variable. So the expected value of x bar is going to be equal to the expected value of 1 over n sub I. And we can pull out constants from the expected value. So I can say this is 1 over n times the expected value. And then you can also pull summations out of expected values. So I can say this is 1 over n times the summation. And then I know that the expected value of x is the mu of x. So now I'm going to have n times that expected value. So I can write this as 1 over n times mu of x. And my n's are going to cancel. And my expected value of x bar is just going to be that mu of x, the expected value of x. So that hopefully makes some sense. But then the thing that we're more interested in than the expected value is really the variance of that random variable. And so that's going to be the variance, and I'll just write it again, 1 over n sum I equal 1 to n of xi. And then the trick is that when you pull constants out of a variance, you have to square them. And then you can pull out summations as well. Those don't need to be squared. The variance of x sub I is going to be the same every time. So we're going to have n times that variance. So I can substitute in n for that summation. So I've got 1 over n squared times n times the variance of x sub I. And one of my n's cancels here. So I've got 1 over n times, and then the variance of x we defined as variance of x we defined as sigma of x squared. And then and we could write that if we wanted to as sigma of x squared over n, just to make it a little neater. But then the thing to remember is that the standard deviation is the square root of the variance. So if I want the standard error for x bar, I'm going to take the square root of the variance, which is sigma x squared over n. And I could rewrite that as sigma of x over the square root of n. So that's the standard error formula for a single mean. So the central limits theorem says that if n is large, then that x bar value is going to fall follow a normal distribution centered at mu with standard error sigma over the square root of n, where we're going to define large, for n is large, as n greater than or equal to 30. If you have a smaller sample size, sometimes it's okay as long as the underlying population is kind of symmetric and bell-shaped, but we don't usually know that about the population. And then just like we had a problem with 6.1 where we were trying to figure out about a proportion and we didn't know the true proportion, here we don't know the true sigma, so we have to approximate. So because we don't know the population standard deviation sigma, we're going to estimate it with the sample standard deviation s. So we can say that the standard error for x bar is the sample standard deviation divided by the square root of n. Now, the only thing that happens here is when we start approximating sigma with s, that's going to change the distribution of our statistic from a normal distribution to a student's t-distribution. And the t-distribution looks a lot like a normal distribution. It has these slightly fatter tails because there's a little more uncertainty out at the edges. So we have normal distributions where we often would characterize them, n, 0, 1, and that meant that the mean was 0 and the standard deviation was 1. The t-distribution just has one parameter, the degrees of freedom. So we might put t, 99 for 99 degrees of freedom. And we're going to learn how to calculate degrees of freedom based on the sample size. The degrees of freedom calculation is going to depend on the type of parameter we're doing inference about. So this section, we're thinking about a single mean, and the degree of freedom calculation is pretty easy. It gets more complicated when we do more complicated parameters. As the degrees of freedom increases, or as n approaches infinity, then that t-distribution is going to approach a normal distribution. So if we have a really large sample size, they're going to be basically the same. So I'll just show you this picture here. So the black line is a normal distribution. And then the red line is a t-distribution with 5 degrees of freedom. So you can see that it's a little bit shorter than the normal distribution at the top. It's a little bit fatter than the normal distribution at the tails. And then this blue line, which is sort of in between, that's a t-distribution with 15 degrees of freedom. So even that small increase in the degrees of freedom has made the distribution get closer to the normal at the top and closer to the normal at the tails, but it's still not quite there. And as the degrees of freedom increases, that t-distribution is going to approach the normal distribution. Oh, this picture got rotated. So there is a famous statistician named William Seeley Gosset, and he's the one who came up with the t-distribution. He's shown in this picture holding a beer because he worked at the Guinness factory, and his job was to make sure that the beer was really consistent. So he developed a bunch of statistical methods for sampling, essentially sampling beer. And he came up with the t-distribution while he was doing that, but he wasn't sure if Guinness was going to like it that he was sort of doing his own statistical work. And so when he published it, he didn't want to put his name to it. So he just said that a student had done it. So that's why it says like a student's t-distribution. That's because that was the sort of pseudonym that he was using, his pen name, when he published his results. So the final thoughts for this 6.1D, if we have a large sample size, n is greater than or equal to 30, we can approximate the sampling distribution for a mean using a t-distribution with n-1 degrees of freedom. So this x bar minus mu 0 over standard error is going to follow a t-distribution with n-1 degrees of freedom. And the way that we're going to calculate that standard error is s over the square root of n.